That the question. A copper rod of area 2 mm squared is subjected to different forms of loading as shown. If the Young's modulus of the rod, is given as 110 giganewtons per meter squared, calculates the total elongation of the bar. Okay, so as can be seen here, this load or this bar is actually subjected to different kinds of loading. I've explained to you what compressive loads are, compression and tension loads are. When a load is said to be in tension, the load is pulling out of the given material or out of the surface. Like this is pulling out, so it's a tension force. But this now, if you consider between B and C, consider this bar, then this load is what? A compressive load. A compressive load is a load that pulls inwards towards a material. It's called compressive. But tensile pulls out of the material. So this bar now is subjected to different forms of load. Here is 100, here is 20, here is 10, and here is 90. And you're asked to find what? The total elongation. But not forgetting, it was stated that the copper rod has an area, and the area is what? 2 mm squared. So it means that this is the area of what? The entire copper rod. So area is what? The same for all of them. That's the very first thing you have to establish. Because from here you're seeing that there is no diameter that is given to us. We weren't given diameter, but we are given length. No diameter. So which means the area is what? Synonymous with all of them. They are the same. So the question says a copper rod of area. So you put down the area. Area A is simply 2 mm squared. And of course, you have to convert millimeter towards meter. To convert this to meter, what will you have? To the power of -6, not power 6. Please take note. I wanted to see those that will fail it. Somebody is telling me 0.00. Please. This is millimeter squared. Since it's millimeter squared, normally meter squared, and when it's millimeter, 1 millimeter gives us what? 10 to the power of what? -3. Is that clear? So which means 1 millimeter squared is simply what? 10 to the power of -3 all squared. That will simply give us 10 to the power of what? -6. So 2 millimeter squared there is simply 2 by 10 to the power of -6 millimeter squared. This becomes the area of the surface. Still the same question, they are asking us now, find what? Total elongation. And I've told you that the very short cut is this, that total change in length is simply what? We have F all over Young's modulus into the first length AB, all over what? Area of what? AB, plus length BC, all over area BC, plus length CD, all over area CD. But in this case now, these areas are what? The same. Is that clear? The areas are the same. So simply, area of AB is equal to area of BC is equal to area of what? CD, and is given as what? 2 by 10 to the power of -6 millimeters squared. This becomes the area. The area is the same thing, it doesn't change. Now, another thing that changes here is what? The force. Is that clear? Each of them have what? Different forces. So, which means this force cannot be outside, because the force now is different for each of the materials. It can't be outside. So, each of these portions, A, B, BC, have their own what? Forces. So, we need to send this force inside. That means that we can write this equation as simply change in length is now equal to 1 all over Young's modulus times area. Area is common. So, break out all the areas outside because it remains the same. So you simply have into, if areas comes out, that means you're left with what? Only lengths on top. Is that not so? It means you're left with only lengths on top. Therefore, you have, force and length. So force goes inside. This becomes force of portion AB times length of what? AB plus force of portion BC times length BC plus force of portion CD times length CD. This becomes the total change in length. That's all. The area is the same, it doesn't change. Since it doesn't change, simply pull out the area. All of them are the same, bring it out. Now the forces changes because this is subjected to different forms of loads. All we need to do now is, what is now this force AB, what is force ABC, and what is force CD. Let's now find out. Now to obtain these forces, the bar has to be in equilibrium. To obtain the forces, the bar, each of the segments, each of these bars have to be in equilibrium. Then, how do we put these bars in equilibrium? It's very simple. Now, watch. Let me consider the first bar. Consider bar AB. Let's bring out bar AB. Now, we simply have this. Okay. We simply have this for that bar. On this side of the bar, we simply have a 100 kilonewtons force acting here. So this is the 100 kilonewtons force. And this force is what? A tensile force. A tensile force is actually what? A force that pulls outside of what? A given component. It pulls out from the surface of the component, not inside. If it pulls inside, then it's what? Compressive. And compressive forces are negative, while tensile forces are what? Positive. Beautiful. So if I have 100 kilonewtons here, this is AB, that means for equilibrium to be achieved on this bar, how many kilonewtons must I have here? 100. For equilibrium to be achieved, if I have 100 here, it means I must also have what? 100 here, and it must also be what? Tension. How then do we get this tension force? Now, this is a very simple thing. Look at this thing now. On this portion, I have what? 20 kilonewtons going this way. Is that also? Bring it out. 20 kilonewtons. And again, watch. If you consider just this portion now, this force is it in tension or in compression? In tension. So which means it's positive, right? Beautiful. But look at this other load here. From this end, is this load in tension or compression? Compression. Which means compression is what? So you simply put back here minus 10. And then the final load you have on the system, is this load in tension or compression? And its value is going to be what? So simply plus 90. If you do this whole value together, what will you have? 100. Simply 100. So the beam is now in equilibrium. So which means the force of AB simply was 100 kilonewtons. Is that clear? Okay. So you see, apply the same principle to obtain what? The forces of every other what? Bar. So let's move to portion BC now. Now consider bar BC. So if we move to portion BC, we simply have here this is B and this is C. So we are now at B and C. This force, if you consider that from the idea of B or from the angle of B, is this force compressive or tensile? Compressive. So which means we have this force pulling into what? This surface. So which means that force is compressive. And if this force is compressive, what's the value? 20. The value is 20, but for compressive force, you have what? Negative, right? So that's simply minus 20. You have here minus 20. But that is not the only force we have on this portion. We still have a force behind. This force, is it in tension or compression? What is the value of tension? Plus. So you simply have what? Plus 100 on that face. Plus 100. So minus 20 plus 100 is what? So you simply have what? 80 kilonewtons. So the load on this surface is what? 80 kilonewtons in compression. So which means automatically I must also have what? 80 kilonewtons here. Is that clear? Now to prove this, in this portion, is this load compressive or tensile? So which means you're going to have what? Beautiful. So we have then this becomes minus 10. And then on this end, is this tensile or compressive? Which is going to be what? Plus 90. So minus 10 plus 90 is what? 80. Sorry, this is going to be coming in what? So you have 80 kilonewtons. So which means that this is under compression and the load is simply what? 80 kilonewtons. I hope you're all following. Yes, okay. Finally, we obtain the tension from the first word by CD. So simply consider by CD. Consider by CD. So we simply have there. This is C and this is D. And the only load we have for this bar is at this point. This load here is what? 90 kilonewtons. And this load is in tension, right? So which means this bar literally should be what? Under what? A tensile force. Okay? So you simply have that load to be 90. So we have there 90 kilonewtons. So it means that we also have to show them that this bar is under tensile force of 90 kilonewtons. But how? Let's now show them. Okay? So if you consider on this portion, If you now consider from the idea of what CG, is this force intention or compression? Tension. Which means the value is what? Okay, so you simply have plus 10. So put it down there, 10. And then, if you watch from this angle now, is this bar in compression or tension? Compression. The value is what? Minus 20. Why this is what? In tension, right? The value is what? So simply minus 20 plus 100. Minus 20 plus 100. And of course, 10 minus 20 is simply minus 10. Minus 10 plus 100 gives you what? 90. 90. So this bar is actually under 90 kilonewtons force. That's all. That's how you obtain the forces. It's as simple as this. So if you know this, therefore total elongation, change in length is now equal to, for the formula, we simply say 1 all over Young's modulus times area. So we simply have 1 all over Young's modulus is given as 110 by 10 to the power of 9. The area is constant, that's 2 times 10 to the power of minus 6. Okay, into so force AB times length AB, and force AB gave us what? 100 kilonewtons. The length AB is simply what? 10 millimeter. So simply 100 by 10. So we have here 100 by 10 by 10 to the power of minus 3, converting that millimeter to meters. Next is force BC times length BC. The length of BC is simply 15 millimeters. Force BC will obtain the value at 80 kilonewtons. So please, this is kilo. Kilo is also times 10 to the power of 3. So 100 by 10 to the power of 3. Okay. Alright, so plus force BC is 80 kilonewtons. So 80 by 10 to the power of 3 times the length of portion BC is 15 millimeters. So 15 by 10 to the power of minus 3. Okay. And finally, plus the last load CD times length CD. And that simply gave us the length of CD is 10 millimeter. Yes, 10 millimeter. So you simply have here, load CD is 90 kilometers. So you simply have 90 kilo is times 10 to the power of 3. The length is 10 times 10 to the power of minus 3. So whatever you obtain here becomes divided by this whole value. That simply gives you a total change. It's as simple as that.
Sir,
yes.
But you can still solve
individually, yes.
Yes.
But it will take you time if you do that. Yes, you can. Highly possible. I saw the question like that on my YouTube channel, and it took me almost 40 minutes. Yes. But if you're solving them individually, you know what you pass through to solve them individually. Change in length for the first material is simply what? Force times length all over area times Young's modulus. Do this for the first material, do this for the second material, do this for the third material, and then you add up together again. It will take you to actually consume your time. Okay. Alright, so this is something you should consider. Please, what's the value? Give me the total answer.
0.01
0.01
409
409 millimeters. So this becomes total elongation. So as simple as this. That becomes total elongation. Okay.